Okay, so I recommend that you go back through this and make sure you understood section 1 of chapter 9 and also section 2 of chapter 9. And this is what we wrote on the board, that the expected value is just for a random value, a random variable that has these values with these probabilities. So remember that each value for the random variable has probabilities. And so to calculate the expected value, we showed this formula on the board. So if this is not perfectly clear to you, then just go back and make sure you read this section 2 that I distributed. So here's the, again, what we wrote. Actually, I wrote a sigma here, and I wrote px, or actually I think I wrote xp, but here they're not writing with the sigma. That's the only difference. So let's try that here quickly. So it says, if x is the number showing on the top face when a fair die is tossed, then as shown in example 2, the expected value of x. Now this is just another notation for the expected value of a random variable. So mu means the mean, and here we're talking about mu of the random variable x. So you can write it this way or you can write it this way. In any case, this is exactly what we showed on the board, that it's 3.5. I think we got 21 over, I think we got, 18 over 12. No, that's not what we got. But anyway, we got 3.5. Okay, so here is an example 7 of the first section. So you can go back and check this. But they're saying, suppose that we have a random variable x denoting the number of defective resistors in a sample of 2 resistors from a production process in which 5% of all the resistors are defective. Find the expected value of x. So we need to think about what the possible values are for x and their probabilities. So the expected value means the possible values for x are, we're taking 2 resistors, so we might have none of them are defective. We might have one is defective, or we might have both are defective. So the possible values are none, which is 0, 1, or 2. So those are the values for x. Now we need to figure out what are the probabilities for each of those. What's the probability that none are defective? What's the probability that 1 is defective? And what's the probability that 2 are defective? Now, they already did this in the previous example in section 9.1, and they found out that the probability of 0 defective is this number, and the probability of 1 being defective is this number. So this is much more than this, and the probability that both are defective is extremely unlikely. It's this number. So you can go back and check the calculations there. So now we just have to do this calculation. The expected value is we take each value of x, and there are only 3, 0, 1, and 2, times their corresponding probabilities. That's this, this, and this, and apparently you get this. So we can say the expected value is 0.1, and you can also write it like this, or maybe even like that. If you don't want to carry around the x there, you can just drop it if people know what you're talking about. Okay, let's do another one. A businesswoman has 2 investment possibilities, Project A and Project B. So she can invest in 2 different projects, Project A and Project B. If she invests in A, there's a 20% chance that she will lose $10,000, a 70% chance that she will break even. That means she won't lose anything, she won't gain anything, and a 10% chance that she will make $200,000. So let's say these are like kind of her profit. So she could make, we'll ignore how much she's investing. This is just how much profit she makes. So 200,000 or break even, 0, or lose $10,000, minus 10,000. So we can think of this as a random variable, the amount of money that she will end up with. So she might end up losing minus 10,000. She might end up with 0, or she might end up with 200,000. So those are the three values of the random variable. This random variable representing project A, we would say only has three values, three possible outcomes. So these are the three possible outcomes. And then we want to put their probabilities, sort of we can draw this tree. So it says that there's a 20% chance that she'll lose. So we could put that 20 here just to make it help us visualize this. And there's a 70% chance that she'll break even. And there's a 10% chance that she'll end up with 200,000. So that is called Project A, but she also has the opportunity to invest in Project B instead. And there's a 15% chance that she will lose 10,000. There's a 25% chance that she will break even, 25% at 0. And there's a 60% chance that she will make 50,000. In which project should she invest? So how can we decide whether this is a better project than this, or whether this is a better project than this? Well, one way to decide would be to calculate the expected value. Now, that's not the only consideration that you would ever want to make when you're considering investing, but it's one factor. So let's consider the expected value for project A and the expected value for project B and see which one is bigger. So remember how you get the expected value. You take the outcome times its probability plus the outcome times its probability plus the outcome times its probability. So for A, for project A, that's the outcome is 10 minus 10 times its probability. The outcome is 0 times its probability, and the outcome, which is 200, times its probability here. So that gives you an expected value of 18,000. Okay, then we can consider project B and also calculate the expected value. Maybe, as I said, it's not necessarily the only way to decide, but it can be interesting or useful. So here we take the outcome here times its probability, that's here. The outcome here times its probability, that's here. And the outcome here times its probability, that's here. And so when we do that, the expected value, we get 28 something. So in terms of expected value, project B is better than project A. Okay, you can also do this for a roulette wheel. So, roulette wheel is for gambling. And roulette wheel has these 36, so you can bet on one of these 36 outcomes. And then there's two more outcomes which they label 0 and 0, 0. Now the way that it works is if you bet $1, for example, on the number 4, and if 4 occurs, then your net win is $35. So in other words, you get $36, but you put down $1. So your net win is 35. So your net win is $35 if you bet $1 on 4, and it lands on 4. If 4 doesn't occur, then your loss is $1. So we could say, what's your expected win for this game? Which will basically tell you what you should expect to win on each dollar bet that you make. So we can do this by defining a random variable, which is the variable which is your net outcome. So we just said that there are two possibilities. Either you win, either the ball lands on 4, or it doesn't. If it wins, your net is plus 35, and if it doesn't land on 4, your net is minus 1. So we can talk about that as a random variable and then ask what's the expected value for that random variable. So we need to know the probabilities for this and this. Now, when you're just looking at the game, you think, oh, the probability is probably 1 out of 36 that it lands on 4, but it's not right, because there's also these two, 0 and 0, 0. So actually, your probability of landing on 4 and getting the $35 is not 1 out of 36. If it was 1 out of 36, that would be called a fair game, but it's not called a fair game. So anyway, there's 1 through 36 plus 2 more. So your chances of landing on 4 is 1 out of 38. So that's the probability that you get 35. And what's the probability that you get minus 1? Well, if the chances of landing on 4 is 1 out of 38, then your chances of not landing on 4 are 37 out of 38. So we have the probability that you get 35 is 1 out of 38, and the probability of losing 1 is 37 out of 38. So now, with those probabilities and these two possible values for the random variable, we can do the calculation of the expected value by taking 35 times its probability and negative 1 times its probability. That's what they do here, and apparently this is it. So if it was a fair, what's called a fair game, your expected value should be 0, but your expected value is not 0. It's minus 0.05. So that basically means that the house, the owners of the casino, will make 5% on every dollar, on every everything that's bet. So if you bet $1, the casino should expect to get about 5 cents. So for every dollar that you bet or anybody else bets on the roulette wheel, the casino will make 5 cents. If you bet $100, the casino should expect on average to make $5. So if many people are playing this, of course not every time the casino will win, but on average they'll get $5 per 100 that's bet. Okay, so that is the idea behind the expected value. So you can go through some of these problems and see if you can solve some of them. And also I provided you with the answers to, I think it's the odd numbered problems here. Okay, so here they have a picture of two different random variables. So this random variable can take on the values -3, -2, -1. I don't know what this is, but it can take on the values -2, -3, -2, -1, 0, 1, 2, 3. And the probability that it takes on -3 is up here. And the probability that it takes on -2 is here. And -1 is here, and so on. So it better be that when we add all these up, that we get 1. Otherwise, there's something wrong. And if we look at y, that's another random variable. It doesn't seem to have any probability that it's -3 or 3. There's a probability that it's -2, which is this number, probability that it's -1, which is this number, and so on. And these better add up to 1 as well, or something's wrong. Now, if you just sort of look at this and ask, where's the mean? You know, these are both, this is symmetric around 0, and this is symmetric around 0. So you can sort of guess that the mean for both of them is the same. Mean for both of them is 0. But like I showed you in class, I think we used a color purple and a color red, and I think the color red looked more like this versus the, I don't know if the purple one looked like this, but the color red looked more like this. And the point was that the red distribution was more tightly packed around the center than the other one, than the purple one. And that's also the case here. This is more tightly packed around 0 than this is. They're both symmetric around 0, but this one is more spread out. And that gives us the concept of the standard deviation of x and the standard deviation of y. And this one is more spread out, so we will come to say that x has a larger standard deviation than y does. So where does that come from? So we're going to consider x minus mu. Remember, mu is the center, so in fact, in this case, mu is 0, but generally it doesn't have to be 0. But we're going to look at how far all the x's are. So So this from 0, and this -2 from 0, and 1 from 0, and 2 from all of those, times their probabilities. So that's like the weight. How much weight should I give this 3? Well, 3 is how far from 0? It's 3 units from 0. But how much weight should I give that 3 units from 0? Well, it's pretty big weight. It's 30%. 30% of the cases will be 3 units from 0. And also 30% of the cases down here will be minus 3 units from 0, so to speak. So what we want to do is find out how far, we want to consider how far each piece is from 0. So that's what this is doing. How far is each one from the mean, in this case 0. And that's called the deviation of x from the mean. But we want, oh, and we're also going to square that for reasons similar to other times that we square things, because we want to avoid cancellation. Basically, we want to get rid of negative numbers, so we square it. So, okay, we'll square it. And then we want to weight that according to the probabilities. So for I want to say, how far is this from 0? I'm going to square it, and then I'm going to multiply it times 30%. How far is this from 0? I'm going to square that, and I'm going to multiply that by 0.05. Did I say 30%? I hope I said 30%. This is 5%, and 5%, and so on. So what we're going to do is take each value, see how far it is from, this is a different example, sorry. We're going to take these and sum them up. So let's see the formula. And I suggest that you read this. This gives you the intuition, but I'm trying to give you the intuition without going through all of this. But here it is. So we're going to take each possible value of x minus mu, minus, it's the center for x, square it, because we want to get rid of cancellation or get rid of negatives, and multiply that times its probability, times the probability of x1. And then the same thing for x2. How far is that from mu? Multiply it times its probability. And we're just going to sum these all up. And that's called the variance of x. And hopefully you remember that the standard deviation is just the square root of this. So square root of the variance. So when we talk about the variance of x, this is what we mean, where x is a random variable. And we can also, so that hopefully they show that here. So the standard deviation of x, that's this, is the square root of the variance. So it's the square root of this stuff here. So if you want to just read this, let's try it. Let's figure out what is the standard deviation for a die, or for the the number of dots that appear on the top of the die. So an experiment consists of tossing a fair die and observing the number x showing on the top face. So x can be 1, 2, 3, 4, 5, or 6. Use the well, they say use the approximation, so I don't want to do that. But here they're not really using this this approximation. So what do? We take 1 minus. So we need to know the mean first of all, and that's the expected value. We need to know the expected value of a die, but we already talked about that, or you can redo it. It's going to be 3.5, which is right in the middle between all the values right here, 3.5. So that is the expected value. So that's mu. We can also call that mu. As I said, that's just another name for expected value when we're talking about random variables. So we have to take x minus the expected value. So I'm sorry, 1 minus the expected value, 2 minus the expected value, 3 minus the expected value, 4 minus, 5 minus, 6 minus. And we need to square each of those. And then we need to multiply them times their associated probabilities. So the probability of 1, probability of 2, probability of 3, 4, 5, and 6. In this case, they're all 1, 6, 1, 6, 1, 6, 1, 6, all of them are 1, 6. And so what do we get when we do this? The variance is when we do all this calculation, we get 2.92. So that's called the variance of the um, random variable, which represents a die. And then, typically we want to get not the variance, but the standard deviation. So we'd have to take the square root of that. So again, the notation is sigma sub x for the standard deviation of x, or if you want the variance, it's variance of x like that. Now you can show that there's another way to do the calculation. Instead of doing it the way they did it up here, or sorry, up here, you can do it. You can show algebraically that you can say that this is equal to this. So it's just a little bit of algebra, but sometimes this is easier to use. But anyway, we don't need to use it in general. Okay, so let's just quickly review some ideas here. So we talked about discrete random variables, and we talked about probability distributions. Let's just go over that a little bit more. So here we can have, suppose a couple plan to have 3 children, and they're interested in the number of girls they might have. This is an example of a random variable, and customarily denoted by a capital letter. So this could be a random variable. So x would be the number of girls, and then I want to ask, well, what are the possible values of x? And it could be 0, 1, 2, or 3. And then we can ask, what's the probability distribution for this random variable? That means we want to know what the probabilities are for each of these. Now, we can first draw the sample space like this. So we can have boy on the first, boy on the second, boy on the third, or boy, boy, girl, or boy, girl, boy, and so on. And there are 8. This is just like tossing a coin 3 times. There are 8 possibilities there. Here they're B or B or G. There they were H or T. So, however, we're not going to assume that these are equally likely. That is, we're not going to assume that boys and girls are equally likely, because actually in reality they're not. So here I think somewhere they tell us that the probability of a boy, well, here I think it's a boy is 52% and girl is 48%, or it might be the other way around, but they're not equal. So the probability of BBB will not be the same as the probability of GGG. Now remember that that we can treat each of these as an independent event. So getting a boy on the first child, getting a boy on the second, getting a boy on the third, they're independent. So we would have to, we could multiply. Remember, when we have independent events, we can multiply their probabilities to get the probability of the compound event. So this would be 0.52 times 0.52 times 0.52. Apparently that's this. And this would be 0.58 times 0.48 times 0.48 times 0.48, and that would be this. And the rest of them are done in a similar way. Now remember that a random variable is a mapping from the sample space to a set of numbers. And here the set of numbers are 0, 1, 2, and 3, because x is the number of boys, and that's the these are the only possibilities for the number of boys. And then we want to figure out, well, what's the probability of 0? Well, there's only one way for that. So it's 0.14. What's the probability of 1, though? There's actually 3 ways for that. You could have a girl on the last child, a girl on the middle child, or a girl on the first child. So there's 3 of those. So they've highlighted that here. And those 3, you have to add them up to get the probability. So it's 0.13, 0.13, 0.13, 0.13, which is this number here. For 2, it's this number, and for 3, it's this number. So this is called the probability distribution for this particular random variable x. And then we could ask a question like, what's the probability that x is less than 2? That means that in this case, x we just said is the number of boys, so it means the probability that the number of boys is less than 2. So that equals, there's only 2 ways that it can be less than 2. It's if you have 0 boys or if you have 1. So you can figure out each of these. In fact, we already did that. So we would add them up, and we would get these numbers here, and we would get that. So that's the answer to this question. Now, like I said in class, I like to put kind of quotation marks around this because that this is kind of the name of an event. The event that you get less than 2 boys is an event, but we find the probability like this of that event. And here's a picture of 0 boys probability. This is probability axis. 1 boy, 2 boys, and 3 boys. So less than 2 is these two, so we'd sum those up. This is called a graph of the probability distribution for x. So in basic probability, in basic statistics, we talk about the mean and the variance of data, and here we talk about the mean and variance of random variables, which are sort of related. I mean, definitely related, but it's not exactly the same setting. So let's read what they say. They said in chapter 2 we calculated the mean and the variance. This is the variance. S is the standard deviation, so S squared is the variance of a sample of observations. So that's just like some data from its relative frequency distribution. So they did it that way. Here, I think we might have done it that way. Well, no, we didn't do that in our class, but hopefully you've done that before. In the same way, it's natural to calculate the mean and variance of a random variable from its probability distribution. So I would like to go back to here, chapter 2, and show you that. But this is from the book called Wanacott and Wanacott, and I did give you access to that book, so you could go back and look at it. I don't want to go and do that here. I'm assuming that you've done calculations of mean and standard deviation, which I'm sure you have, but I'm also assuming that you can do it using the relative frequency here. And for that, you might want to go back and look at chapter 2. So anyway, here, the mean, which we also call the expected value of x, we call it the expected value of x, or the mean of x of the random variable x, and is x p of x. So we covered that in the other book, so I'm not going to repeat it again. And this is the variance of the random variable, and this is very similar to the formula that we have for the variance of data. So here it's x minus mu. This mu is this mu. X minus mu times the probability. So this is like a weight on this. These are like we weight each of these. We're summing up a bunch of these, and each one is weighted by its own probability. Same thing here. We're summing up a bunch of these, and each one of these is weighted by its own probability. We're summing up across all the different values of x, and we're weighting those by their probabilities. So the probabilities are the weights. And here they say, here we are following the usual custom of reserving Greek letters for theoretical values. Mu is the Greek letter mu, equivalent to m for the mean, and sigma is the Greek letter sigma, equivalent to s for standard deviation. So here they're saying we use this for the sample of the mean of just some data. So we take each piece of data, how many times did it occur, divided by the total number of times that it, for all of the total size of our data set. So this is the relative frequency of each value, and that's pretty obvious that this is what we mean by the mean. Anyway, the symbol here for the mean of data, we use this, but when we're talking about the mean of a population or the mean of a random variable, we use mu instead of x bar. And similarly here we use s squared for this one and sigma for the population variance or the variance of the random variable. So as the population is kind of theoretical because we assume that we can't know the whole population. That's kind of what we mean by the population is sort of like too big to know it. That's the whole reason we do statistics, is because we take samples, because the population we assume is too big to deal with all of it at once. Otherwise, we wouldn't take a sample. So that's a theoretical value. That's why they use, in that sense, it's theoretical. That's why they use sigma and mu. And the random variable is also theoretical. If we go back to that example of the number of girls, not specifically for a particular family, it's sort of theoretically what are the probabilities for 0, 1, I'm sorry, number of boys, 0, 1, 2, or 3 boys. That's kind of a theoretical, it's not for specific data, it's just in general. So we can say that's also theoretical. So in both cases, both populations and random variables, we think of them as theoretical, and therefore it's standard to use Greek letters for that. So instead of S, we use sigma and so on. So going back to it is the number of girls, not the number of, sorry, I said it was the number of boys, it's the number of girls. But going back to that question, we can calculate the mean, the variance, and the standard deviation for this random variable. And you can check some of these calculations here. Sorry for this, the way this comes out. But you can check some of these to see if you understand the idea of what's going on. Okay, so that was for the number of girls, and there were only 4 possibilities for the number of girls. 0 girls, 1 girl, 2 girls, and 3 girls. That's four possibilities, including 0. However, other random variables are not limited, don't have a finite number of values. They can have an infinite number of values, and they can have a continuous infinite set of values. So that's like they can have all the values on the real number line. For example, we can talk about people's heights, and somebody could be 160 centimeters tall, or they could be 160.1, or 160.11, or 160.111. So in a sense, it's infinite number, and that infinity is represented by the real number line. In that case, we call that kind of variable a continuous variable, and the distribution, the probability distribution for that variable, is a continuous distribution. So in other words, we can't use a graph like this. Here, where we only have 4 possibilities, we're going to have sort of a graph for every possible value on the x-axis. So that's you have to treat things differently because of that. Because here, notice that when we add these up, we get 1. But if I said, oh, I'm going to draw some kind of shape here, then when you add them up, you're going to get 1. Then that's never going to work, because we're basically never going to work, because you're going to have too many values to sum up to just 1. So here they kind of try and bring us into this idea slowly. So here we have men's height in feet. A foot is like 1/3 of a meter approximately. So here's a 6 foot, the number of people who are 6 feet tall, and I guess this is, I don't know, some fraction between 6 and 7. Anyway, this is a bar graph, and then we can rescale that. So we can, but basically what we'd like to do is take this, where the area of all these blocks is probably not equal to 1 right now, but we can rescale the y-axis so that the area of all of these blocks together will be 1. You just divide by something. What do we divide by? Well, let's not worry about what we divide by, but you divide by something, and that will, whatever the area was here, let's suppose the area was 2. Probably not 2, but suppose the area was 2, then if you divide these numbers by, I think if you divide them by 2, then the area will be 1, or something like that. But once we do that, this was originally the relative frequencies, but then when we divide it, we call it the relative frequency density, because they're not the relative frequencies anymore because we changed the scale. By the way, you can see here this is not really scaled, right? This is from 0 to 5, and then this is 5 to 6. There's something wrong there, right? This is only length 1, and this is of length 5, but they put this little thing in there to say it's kind of rescale. They just trying to show everything cleanly. Okay, so anyway, but the most important thing is here, this is called the relative frequency density. And then what they can do is they can divide those intervals. Here we only had like an interval from, how many are there here? 1, 2, 3, 4. I think there's 4. I think these are divided into quarters, but we can divide them into tenths. So each one will have represent a smaller interval of people's heights, but we can do that. We can just divide, and we'll get more bars here. And the bars will actually get shorter, won't they? Because if this is people between 4.75 and 5.25, and this is only between 4.9 and 5.1, then you're not going to have as many people. So the bars will get shorter, but you can again keep rescaling if needed, so that we may not need to rescale. But anyway, this is still called the relative frequency density. And then what we do is we keep dividing the bars. Here maybe they didn't divide it as much as here. Here they divided more, and here they divided more. And we can sort of imagine that we keep dividing the bars, the interval into more bars. And so finally we get like a smooth curve. And then that is called the probability density function. So this thing here, this curve here, is called the probability density function. Okay. So the thing is, though, that once we get this probability density function, whereas here we could say, oh, the height of this bar tells me how many people are in this interval. Now I don't have intervals anymore. I've sort of made it the number of intervals infinite, so I really don't have intervals anymore because they got so narrow that there's not intervals anymore. And so I can't, I don't look at the height per se anymore. So what I can do, though, is I can say, well, how many people are in this between here and here? And that's going to be, it turns out that's going to be represented by not the height of this or the height of this, but by the area under the curve here. So some amount of area here, and that will, remember that basically we changed things around so that the total area was 1, and we still maintain that here. So the total area of this is 1, so the probability that someone is between here and here is going to be the area under here, which is going to be some fraction of 1 of the total area. So you can slow down this video and read what they said in each step here, but that's the idea. So to use the probability density function, you don't look at the height, you look at the area under the curve. And I will slowly scroll through this so that you can read this if you want. Okay, now here's an example of it. So this is a random variable called t, and it's not going to be a discrete random variable like the number of girls. Remember, the number of girls could only be 4 different values, but here this is going to be time. The time is typically not discrete, so the total time t that I wait for buses on a long trip that includes a transfer has the following probability distribution. So the time that you wait, we're going to think of that as a continuous random variable. It could take any value, like between 5 and 10 minutes, could be anything between 5 and 10 minutes, not just 5 minutes, not just 6, not just 5, 6, 7, 8, 9, 10, but anything in between those values as well. So that would be called a continuous random variable. And since it's a continuous random variable, again, we don't say, well, what's the probability that it takes 5 minutes? We don't get that. We don't do that by looking at the height of this. Um, we could say though, what's the probability that I have to wait between 5 and 10 minutes? And that would be the area under this curve. Let's just make sure that the total area under the curve is 1. Can we do that? Let's see, this is, how much is this, the area of this? This is 5 times 0.5, or 0.05. So that's 0.25. So the area of this is 0.25. The area of this is 0.25, so that's half, that's 0.5. And then this is half of 0.25, half of 0.25, half of 0.25, and half of 0.25. That's another 0.5. So the total area under this is 1. So this is what we call a valid probability distribution. Or actually, I should say a valid probability density function. So this is a valid probability density function. And now if I want to read off, what's the probability that it takes less than 5 minutes? That's the area under this curve here. So what is the area under that curve? Well, I just figured out that the area under this was 0.25. This is half of that, so it's 0.125, right? So that's the area in here, and so that's what we would say is the probability that we have to wait 5 or fewer minutes, or between 0 and 5 minutes, for the bus. If I want to know what's the probability that I have to wait between 5 and 10 minutes, it's this plus this. It's the area under this part of the curve. So that's this area here. So that's we already said this is 0.25, and this is half of that. So it's 0.375, I think, or yeah, I think that's right, 0.375. Okay, so that's how we use a probability density function. We don't look at the height, we look at areas under the curve. So here's just another one. If I wait more than 15 minutes, I will be late for my appointment. So if he has to wait more than 15 minutes, he's going to be late. So what's the probability that he's going to be late? So that's the probability of more than 15 minutes, and that's here. So what is that? We already said that's 0.125, or 12.5%. Okay, here's another example of a continuous random variable as opposed to a discrete random variable. We talked about the discrete was the number of boys or the number of girls, but then we talked about a continuous one, which is the amount of time that you wait at the bus. And here's another example, also using time, of a continuous random variable. At a busy switchboard, the waiting time t, so it's time, waiting time, switchboard. So between one incoming call and the next was recorded thousands of times as follows. So this is an approximation of what actually happened. So so this would be called, they're calling it a relative frequency density, but it's also a probability density function. So we want to, so we can see that this shape is, of course, different than the last example, which looked like a pyramid. But here, this is also, hopefully, the total area under this curve has to be 1 in order to be called a probability density function. Okay, so assuming that that's true, estimate the probability that t exceeds 30 seconds. So that's kind of hard to do, but I don't know exactly how they want us to estimate this area. But let's just say here, suppose I wanted to know, this is 10 seconds, so this is 2 seconds, I guess. So between 0 and 2 seconds, we could say, what's the probability of that? And so we would take, this would be 2 units, and this would be 1, 2, well, 0.5, 0.6. So the area just here is, I'm sorry, 0.05. So 0.05 times 2 is 10. So that's that's the area here. So this is the area here is point, 0.12, and then there's a little bit more. So we could say it's about a half. So it would be 0.13. So we could estimate that the 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 number of seconds between two calls, the probability that it takes about 2 seconds between a call is what we just said, 0.13, 13%. I'm not quite sure how they want us to do that. So we have to kind of estimate the area under here. So I'll leave that alone. Okay, next we talk about the normal distribution, which is also a probability density function, just like this is. So it has the familiar shape of this, but it's also, just for our purposes, just another example of a probability density function. That means that the area under it should be 1. Well, as long as that's the case, then that would be called we could call that a probability density function, and we could say it represents maybe the probability that people, or whatever it could be. It could be anything, lots of different things, but it could give us probabilities, just like we got a probability in this case. That was the probability that it took 2 seconds, that there was a 2-second interval between one call and the next. Okay, I'm jumping to chapter 5 here in this book, and we're going to talk about joint distributions. So that's when we have two random variables. So here we have one random variable is the same as before, the number of girls, and the second they call the number of runs. So what do they mean by the number of runs? So here, this was the sample space before for the number of girls. So here we say we have a run of boys and then a run of girls. It's a little hard to understand that when you only have three people or 3 children or three births. But suppose you had 5, then you could have like a run of boys and then 3 girls. That would be called a run of girls. So even in this case, even though there's only 1 girl, we'll call it a new run. So we have 1 run and then a new run. So here we have only 1 run. Here we have 2 runs. Here we have 3 runs. Here we have 2, 2, 3, 2, and 1. So that's what we can mean by the number of runs. So the number of girls is 0. The number of girls is 1. The number of girls is 1. So we have 0, 1, 1, and so on. But the number of runs is 1 here. So we put, that's the y variable is the number of runs. The number of runs here is 2, so we put 2 there for y, and so on. So y can range from 1 to 3, and x can range from 0 to 3. Now we can talk about something called the joint distribution. So we can have y across here and x down here, and we can say what's the probability that we have 0 for x and 1 for y. So what does that mean? 0 for x means no girls, and 1 for y means a single run, and that's this case here, and that's 0.14. Okay, so what is this 0.26 for? That's the probability that we have 1 girl and 2 runs. So where is that? So I guess that's here. We have y equals 2 and x equals 1. Let's check. X equals 1. Here, 1 girl. Here, 1 girl. Here, 1 girl. And then y equals 2. Here is 2 runs. Here is 2 runs. Here is 2 runs. And here is 2 runs. But we want the intersection of that. We want 1 girl and 2 runs. So where's the intersection of this one and this one? It's this and this. So to figure out what goes in here, we need to know the probability of this and this, but we have that here, 0.13 and 0.13, so that's 0.26. So that's what this table is telling us, and it's called the joint probability distribution of x and y. So they say we have 2 random variables defined on the same sample space. So it's crucial when we do this that the random variables are defined on the same sample space, otherwise this doesn't make any sense. So going back up to here, in the planning of 3 children, let us define 2 random variables. X equals the number of girls and y the number of runs, where run is an unbroken string of children of the same sex. For example, y equals 1 for this, y equals 2 for this. Suppose that we are interested in the probability that a family would have 1 girl and 2 runs. As usual, we refer to the sample space of the experiment. So we just looked at that. These 2 events are colored, and their intersection has the probability 0.13 plus 0.13, which we denote, and we don't write this like this, we write it like this. I mean, we could write it like this, but it's common to write it like this. So this means what? X is equal to 1 and y is equal to 2. So the comma actually is a substitute for the word and. Right? So what would this mean? X equals 0 and y equals 1. So the old terminology was the probability of G and H, that's using events, or the probability that X equals 1 and Y equals 2. Those are referring to things in terms of basically as events, or the probability that X equals X, little x, and Y equals little y. But here we're talking about joint, we use the terminology of joint distribution. So to rewrite this, we say the joint distribution of x and y, and we say the probability of 1 comma 2 instead of this, and the probability of x, y in general instead of this. So what does this mean? It means this. So again, the comma is for the word and. And here we talked about independent events. The probability of E and F is equal to the probability of E times the probability of F. We did say that at one point. How do we write that in the new terminology? The probability of E and F, we write probability of, we have random variables X and Y, and we want to talk about the X and Y being independent. Now that's saying a lot more than just saying that 2 events are independent. So when we say that 2 random variables are independent, that's not the same as talking about 2 events being independent. I mean, it's a much stronger statement. And what does it mean? So it means that for all x and y, p of x comma y is equal to p of x times p of y. So remember, like here, that would mean that, for example, this p of x, probability of x equals 1 and y equals 2 is written like this, equals the probability of 1 times the probability of 2. But not just that, for every possible combination of x and y values, it has to be true that this equals that. So that's saying so much more than just for one combination, or basically one pair of events. This is for many, many different pairs of events. Let's see if they explain that a little more. So here we have just the probability of x. This is just telling us the notation that this means that. So that's nothing new. We already talked about Okay, to get to here, we have to do a little bit more. I don't know quite why this is like an outline. So we didn't get to here yet, actually. So let's ignore what I just said about this, and hopefully they'll explain it a little bit more step by step. So let's go back to the next section. Okay, let's define what we mean by marginal distribution. So we just talked about the joint distribution. Here's a picture of it. And what do we mean by that? Well, if we go back to the joint distribution, we can see that we have x and we have y. So we can put that here, x and y. So we can have, for example, x equals 0, x equals 1, 2, and 3. So we can have 0, 1, 2, and 3. And we can have y, 1, 2, and 3. I don't think there's any y, 0. And then we can just signify the probability, the joint probability, by the height. So on the z-axis. So for example, this is 0.26. This is x equals 1 and y equals 2. So x equals 1 and y equals 2. So this would be 0.26. This would have a height of 0.26. So that's a picture of the joint probability distribution. And we can also do it this way. So instead of drawing the height, we can just make have the size of the circle represent. So this is the place where the height is the largest. It's 0.26. So this is the largest circle here. It's also 1, 2, 1, 2. Okay, so let's look at this picture. So here we have the whole sample space, and there are certain outcomes where y equals 0, and this isn't necessarily the example of the one that we gave earlier, because here we're allowing for y to be more than the y that we were just talking about, and x is more than the x that we were just talking about. So this is just general. So there are certain elements of the sample space where y equals 0. So that's all of these. This is y equals 0 here. And y equals 1, there are other ones. And y equals something else, there are other ones. And y equals something else, there are other ones, and so on. So we can actually say, we've used this language somewhere before, we can say that these different values of y basically partition the sample space. They form a partition of the sample space. And then we can also do x equals 0. There's certain sample points that have x equals 0, certain sample points that have x equal 1, x equal 2, and so on. So we can also say that these x equals 0, x equals 1, and so on, those are all events. That's what I forgot to say. Y equals 0 is an event. Y equals 1 is another event. Y equals something else is another event. And same thing with x equals 0 is an event. X equals 1 is an event. X equals 2 is an event. So we can say that these different values of x also partition the sample space. And then we can talk about, well, what's the probability that x equals something? They actually write x equals x, but anyway, x equals something and y equals something else. That's the points in here. So we're asking, when we say what's the probability that x equals something and y equals something else, we're saying what's the probability of this. And so this will be denoted by the probability of xy. So here they say this is two random variables, x and y, showing their joint probability distribution derived from the original sample space. And they say you can compare this with figure 5.1, which, remember, looks like this. So here x and y are also basically partitioning the sample space. Here we see where x equals 1 is. If we want to see where x equals 2 is, that's where we have two girls. So that's this one, and I don't know, I think one other one. So anyway, x and y still partition the sample space, just like here. Okay, and we can say, what's the probability that x equals 2? So here's x equals 2, and it's all of these. But we can obviously say that all of these are equal to this, plus this, plus this, plus this, plus that. But what does that mean? That means that the probability of x equals 2 equals the probability of this plus the probability of this plus this plus this plus that. Now, why can we say plus? Remember, we had a rule that said we can say plus when the events are mutually exclusive or they are disjoint. And these are clearly disjoint. This here doesn't intersect with this, and this doesn't intersect with this, and so on. So we can say plus. So that's what this says down here. The probability that x equals 2 is the probability that x equals 2 and y equals 0, plus the probability of x equals 2 and y equals 1, plus the probability of x equals 2 and y equals something else, all the way to the end. And that's what this says. The probability that x equals 2 equals probability of x equals 2 and y equals 0, 2 and 1, 2 and 2, 2 and 3, all the way to the end. In other words, we can summarize this like this using the sigma notation, where y goes from 0 to the end value, whatever the end value is. We didn't write it here. We didn't show it here. And if we don't want to specify 2, but we want to say what is it when probability that x equals 3, we can do this. So this is this statement only involves the x variable. But we got the probability of just something about the x variable by using the joint probability distribution of x and y. And here, what we're saying is the probability that x equals 2 is the sum of all of these. So we can sort of, so that is basically, here's x equals 2. If you want just the probability of x equals 2, you take the sum of this, and this, and this, and this, and this, and this, and this. So here's an example, going back to our original x, where this is the number of girls, and our original y, this is the number of runs. So in that case, x can only go from 0 to 3, and y can only be 1, 2, or 3. The number of runs can only be 1, 2, or 3. So this is the joint distribution. But if I want to know just the probability that there are 0 girls, I can sum these up. That's what we just said. You can sum this up and get to here. So, and the same thing here. If you want to know the probability that x equals 1, you can sum these up. And x equals 2, you can sum these up, and so on. You can also go this way. And you want to know the probability that y equals 1, you can sum these up, and these, to get y equals 2 and y equals 3. So notice that we got the probabilities for x from summing, and we sort of write them over here. And usually, we call this like a margin for the table, a margin for the table. And we also can call this a margin for the table. So from that use of the word margin, they called this the marginal probability. Now actually, we didn't need the joint distribution to find the marginal probability. Remember, that's how we started the whole example about the number of girls. We figured this out before. But we can obtain it from the joint probability by summing to get the marginal probability distribution for x, and also to get the marginal probability distribution for y. So whether we call it the probability distribution for x or the marginal probability distribution of x, the same thing, but it's just, if we got it from here, we could call it the marginal one. And if we got it, again, if we got this from here, we could call it the marginal one. But again, we could also just call it the probability of x. Or I should say the probability distribution of x, as opposed to the marginal probability distribution of x. Either way, you can call it either one. But if you get it from the joint distribution, then they usually use the word marginal. But you can do it either way, but you should be aware what they mean when they use the word marginal probability distribution of x. We can sort of presume that they're getting it from the joint distribution. Okay, so now we can tackle what we mean by x and y are independent. Because at the beginning of this section, I started to go through this, and then now I realized that um, we need to cover some other ideas before we do that. So now we're going to cover what we mean by this is, we know this, that two events are independent if this is true. But now we want to cover this idea. What do we mean by two variables, two random variables are independent? Well, here's the definition. And now we know what these mean because we didn't really know what these meant before. But this is the marginal distribution for x, and this is the marginal distribution for y, right? That's what we've been saying. We can call them marginal. And so this is the rule for what we mean by two random variables are independent. And this is a much stronger statement than saying two events are independent. Let's see that. Let's do it. They say two random variables, x and y, are called independent if the events x equals x and y equals y. Remember, these are events. Well, if we put in a specific value for x here, like x equals 1, that's an event. X equals 2, that's another event. Y equals 1, that's an event. So we can talk about the events. So if the events this and this are independent, but they didn't quite say it here, but they mean for every x and y, not just for one pair of x and y. So not just saying that, um, you know, x equals 1, what does that mean? That means that there's one girl, and y equals 2, what does that mean? There are two runs. Those two events are independent. No, that's not all that we mean. We mean for every possible combination of x and y, when you pair these up, every one of those events has to be independent. So that's what I mean by saying that it's a much stronger statement. It's not just talking about one pair of events being independent. It's every possible combination of events where we generate an event by saying x equals something and another event by saying that y equals something. For example, for the distribution table in distribution table 5.2, that is this one, we can ask, are x and y independent? Now that's a big question. That requires a lot of calculations. We have to say, is when x equals 0 and y equals 1, are those two events independent? What does that mean? There's like an event here, an event here, and they have to be independent. In other words, going back to this picture, x equals 0 and y equals 1, for example. Here's the x equals 0 event. That's one event. Here's y equals 1. That's another event. We want that to be independent, but then we take every other combination. We have to check all of those different pairs of events. So same thing here. We have to take this whole event and this whole event and say, are they independent? And then this whole event and this whole event and say, are those two independent? And so on. Now, how do I get the probability for this whole event? Well, we know it's here, 0.14. And how do I get the probability for this whole event? We know that's 0.25. So we're asking, is the probability of xy, which is here, equal to the probability of x of here times here? So that's saying is 0.14 times 0.25 equal to this. Well, already we see that's not true. So just from that one observation, one calculation, we can see already that these two random variables are not independent. We can check some other ones. For example, just to check, I mean, we've already destroyed it. We've already shown that they're not independent, but we could check, how about this one and this one? So x equals 0 and y equals 2. So x equals 0, the probability is 0.14, and the probability of this is 0.5. So they're just not, this is not working at all. So these two these two random variables are not independent. I've checked two already, and I found that even both of the calculations don't work. That is, I checked this for two different pairs of x and y, and neither of them work. And this says that it has to be true for all x and y. So here they pose the question, and the answer is here. So therefore, thus x and y fail to be independent. That is, they are dependent. So the point here is that saying that two variables, random variables, are independent is a big deal. It's really saying a lot. And we couldn't even get it for even one calculation, but it has to be true for all of the calculations that we would have to do. Okay, here they just give us some arbitrary random variable and, joint distribution table for two random variables. And then they ask us to check to see whether these two are independent. So what would that mean? Well, we have to find the marginal here and the marginal here. How do we find the marginal here? We sum up this to get what goes here. We sum up this to get what goes here. We sum up this to get what goes here, 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 and here. So they do that here. They do all those sums. And now we have to check each one of them. We have to see, is this, that's the probability that x equals 20, which one is x here? This is x equals 20 and y equals 10. So x equals 20, the probability is here, and probability that y equals 10 is here. And we're asking, is this one times this one equal to the joint probability that x equals 20 and y equals 10, which is here. So is this times this equal to that? So this means 1/4 of 16. Yeah, that worked. Okay, so at least one of the calculations works, but we have to check for each one of these. So there's actually 8 different calculations we have to do to see if these two random variables are independent. So they do them all here, and they all work. You can check it yourself, but they all work. So therefore, this since this table Pxy agrees everywhere with the original table P of xy, P of y, is equal to P of x comma y, we have proved that 5-6, which is here, is true for all x and y. Therefore, we can say that they're independent. And then they say, oh, look at this, if you notice this, that this row is a multiple of this row. Is it true? Yeah. 3 times this is that, 3 times this is that, 3 times this is that, 3 times this is that. So that seems like, maybe it's just a coincidence. They say, in example 5.1, an interesting pattern is evident. The rows are proportional. The second row is 3 times the first. The columns too are proportional. Okay, let's check that. So this is, this is twice this, and I guess they're all proportional. The columns are also proportional. And they say this pattern is generally true. That is, whenever x and y are independent, then the rows of the table Pxy will be proportional, and so will the columns. So that's kind of a short way, or an easier way of checking about the independence. Of course, they didn't prove this, but okay. So let's go on to this next section. Now, let's just quickly review some things before we go on. So I wrote some things out here. Actually, I copied some things out here. So what I want to do is first just remind you that, of course, what we mean by the mean for a bunch of data. So if if this was like a 3 and this was an 8 and we had a list of data, like 3, 8, 6, and so on, just a bunch of a list, and a list of data, and we want the mean of that. Of course, all we do, sorry about that, is just add these up and divide by n. This, by the way, just means that's the definition. This is a weird notation, but I just copied it from a book, so I'm just using it. but it just means that's a definition of the mean. So the mean is just, you just add everything up and divide by the total number of elements there. So that's just the mean. And then, well, of course, we can rewrite that like this. Again, I'm sorry for this notation for definition. We can just rewrite this as sum up all the xi, all the x's. That's what this says, sum them all up. And then divide by n. So that shouldn't be anything difficult. And then we also define the variance. Now, actually, I don't want this piece in there. Let me just scratch that out. I don't want this. Let me get rid of that. I don't want to use that form. So just say it's 1 over n times xi minus x bar. So in other words, what we're doing is there's an x bar in our, so let me put that up here. There's an x bar somewhere. So, we have a bunch of data here. So there's an x bar somewhere in there, like, 3, 8, 6, and so maybe x bar is 5 or 7 or something. So x bar. And then we want to measure how far each piece of data is from that mean. So how far, like say x bar was 7, how far is 3 from 7? It's 4. How far is 8 from 7? It's 1. How far is 6 from 7? And so on. So that's what this says. How far is each piece of data from whatever the mean is? So we do that, and then we square it, and we sum that up, and we divide by n. And that's the variance. Okay, so that's what we mean by the variance. Okay, but both of these definitions, these things here and this, are for data, not for random variables. Then we went on to discuss, to learn about random variables, not just about data, and we did define the expected value of a random variable, and we said it was x times the probability of that x. Remember, x can take on different values, like we had the number of girls, and it could be 1, could be 0, 1, 2, or 3. So that's what we say. We have each x times its corresponding probability. Like this one was, maybe, I don't remember what it was, but maybe it was 0.13 or something like that. So that would be 0 times its probability times 0.13 and 1 times its probability. And that's what we're doing here. And we're summing all that up. And that's called the expected value of x. And it's basically like the middle of x. So like, what's the middle of these? Well, it kind of depends on the weights or the probabilities. If this has a big probability and these are all tiny probabilities, then the weight that means we're gonna sort of say that the mean should be closer to 3. So it kind of depends on the weights or the probabilities. So that's why that's what this formula expresses. So that's the expected value of x. Okay, now we also talked about the variance of x. Now, here's what we mean by the variance of x. It's very close to this thing, but instead of dividing by 1 over n, so we have sigma and this minus that squared, and basically, instead of the 1 over n on the outside of the sigma, we have the p on the inside. Please ignore this line here. That's just like I copied a box, and I happen to include the trim around the box. So that's what this line is. So anyway, it's x minus, remember, mu and is the same thing, or it's just another symbol for x bar. Well, more or less. So we have x minus the mean, just like here, x minus the mean, squared, but instead of the 1 over n on the outside here, we have the p of x inside. That is what we mean by the variance of a random variable as opposed to the variance of a data set. Okay, so I just wanted to point out that another way to write variance of x instead of this way, well, compare these two. So this part here is a little bit similar to this part here. What do I mean by that? Well, they both have a p of x there. They both have a, right? They both have a sigma here and a sigma here. So they're a little bit the same. But this part, this one has an x, and this one has an x minus mu squared. So this one has an x, and this one has this. So that's kind of the difference between this and this. This has an x there, and this has this there. Now, what did this x become on this side? It's the expected value of x. So that means that this thing, we can say, is the expected value of this blue, because the expected value of x is the blue, this put over here. So that means that this, I could do it over here maybe. I probably shouldn't have drawn it. I should have typed it. But anyway, this is the expected value of what? If this is the expected value of x, then this we can say is the expected value of x minus mu squared. Like that. Okay, sorry, it's a little messy, but so the this can be written as e of x, then this can be written as e of this thing. So e of this thing. So the variance is the expected value of x minus mu squared. So that's another way. This is one way of writing the variance, but this is another way of writing the variance. So basically the expectation operator, we can call this the expectation operator. What does it do? It takes the thing here and kind of multiplies it times its probability and sigma and sums it up, so to speak. So the expectation operator here takes this thing and multiplies it times its probability and then sums it up. So therefore we can say that the variance is the expectation of this, because it means basically multiplying this times its px and then adding it up. So that's what we have here. So that's what they have here. The variance of x is x minus, I'm sorry, is the, this is not great. Actually, it seems like it would be nicer if they had a square bracket here and a square bracket here. So it's a little bit strange not to have that square bracket. Let me just show you that again. So, you know, I want to have square bracket here and square bracket here, or it doesn't have to be square bracket. I guess it can be open bracket here and open bracket here, or smooth bracket. But, you know, you want to have those brackets around here, but they didn't write that here. So they just put, it's a little confusing actually, because you don't know what this square applies to. Like that, it seems like it applies to the whole E, but that's not right. There's a bracket here and a bracket around here. So the square applies to this thing. It's the way I wrote it here. The square applies to this part, and then we do the expectation of that. So actually this is not so well expressed here. But anyway, there should be an open bracket here and an open bracket here to say that the variance of x is the expectation of x minus mu squared.